Okay, good morning everyone. So in the last class, we discussed about Banach-Steinhaus theorem and the principle of uniform bondedness. So let us see some corollary to that. Look at corollary of principle of uniform bondedness. So let V be a Banach space and W be a nonlinear space. Suppose Tn is a sequence of bounded linear transformations from V into W such that for each x in V, the sequence Tnx is convergent in W. So we are assuming that Tn is a sequence of bounded linear transformation which converges pointwise. So for every x, Tnx becomes a convergent sequence in W. So then if we define T of x is equal to limit of Tnx, then this defines a map from V to W, because we know that limit of Tnx exists for every x. So we can define T of x. This is an element of y. So this defines a map. What can we say about this map? So the conclusion is that then this T is a bounded linear operator, bounded linear transformation from V to W, and also we can give a bound for norm T. Norm T is less than equal to the limit inferior of norm Tn. So what does principle of uniform boundedness say? That says that if we have a sequence of bounded linear operator from a Banach space to a non-linear space such that it is pointwise bounded, then the norm of that collection Ti, that is bounded. So here what we are given is that we have a sequence of this bounded linear transformation, and we are given that limit of Tnx this exists. So if limit of a sequence exists, then that implies that the sequence has to be bounded, right? So this sequence Tnx is bounded. So and therefore by the principle of uniform boundedness, we know that norm of Tn will be bounded. And of course, this T is linear. That is easy to show because Tn is linear, and also limit of the sum is sum of limit for convergent sequences. So Let me write clearly. T is linear. Also, since T and X is convergent, supremum of norm T and X this is finite. So this is true for every X in V. So by the principle of uniform boundedness, we get that our norm Tn has to be bounded. So there exists some m greater than 0 such that norm of Tn is less than equal to m for all n. So remember that for the Banach-Steinhaus theorem, we require only the domain space to be complete. So V is Banach and W is any non-linear space, then this result is true. So we get some constant such that norm Tn is less than equal to this m for every n. So what does this imply? So we have to see so that therefore T will be bounded operators. So norm Tn is less than equal to m. This implies norm of Tnx we know is less than equal to norm Tn times norm x, and norm Tn is less than equal to m. So this is less than equal to m times norm x. This is true for every n. Let me write that for any x in x belonging to V, norm of Tnx is less than equal to norm Tn times norm x, which is less than equal to m times norm x for every n. So we know that Tnx limit exists. So taking limit as n tends to infinity, we get norm of Tx because Tnx limit is t of x. So norm of Tx will be less than equal to m times norm x. This is true for every x in V. And this implies that T is bounded. Therefore, T is a bounded linear transformation from V to W. Now, how to get that norm T is less than equal to lim inf of norm Tn? That again follows from this also. Since norm of Tn of x, this is less than equal to norm Tn times norm x. So we don't know whether limit of norm Tn exists or not, but limit of norm Tn of x, that is the norm Tx. So what we can do is take the limit both sides. So taking limits z tends to infinity, we get norm of Tx will be less than equal to limit of norm Tn times norm x. This is true for every x in V, and therefore by the definition of norm T will be less than equal to this limit. So we get this, that if we have a sequence of bounded linear operator such that it is pointwise convergent, then we get that this limit function that we define, that is also bounded. Okay, so this is one. There is one more corollary that we will do. So let V be a Banach space and let B subset of V be any subset now assume that the image of this B under F, this F of B is a bounded subset of the scalar field. So F is now we are taking the bounded linear functional. So suppose this is a bounded subset of the scalar field. R or C, whatever we have. So if it is a bounded subset of scalar field for each F belonging to the dual of V, then the claim is that V is a bounded subset of V. So note that the converse is of course true, that if we take any bounded subset of V and if we take F to be a bounded linear functional, then F of V, F of B will be bounded, right? Because that is just by the definition of bounded linear transformation, that it maps bounded set to bounded set. So if B is a bounded set, then for every F in the dual, F of B will be bounded set. But here what we are saying is that the converse is also true if V is a Banach space. So to prove this, we will again use this Banach-Stein's theorem. So what we notice is that by looking at the double dual, we know that for every x in V, we have this map Jx which is in the double dual. So for any x in V, consider the functional j of x belonging to V double star defined by jx of any f in V star is nothing but f of x. So what we have seen is that this is an isometry. Then we have seen that norm of jx is same as norm of x. So now what we have, that we are given that uh, this f of b is a bounded subset for every f. So if we take any x in B, we know that if we vary over f of B, that is the bounded. So since f of B is bounded, we have for every x in B, if we look at no, so what we have, well, this is bounded for every f, right? So since f of B is bounded, or any f in V star, we have if we write supremum of jx of f, where x belongs to B, put mod of this. This is nothing but supremum of mod fx for x in B, and this is finite for every f in V star. Right? For every f in V star, where we have supremum of mod of jxf. This is supremum of mod fx, where x is in B, and because we are given f of B is bounded, this supremum will be a finite. So that says that if we look at this collection, uh, jx, this is so now our index set is this B. So we are looking at this collection, and this is pointwise bounded. So therefore, the collection Jx X belonging to B is pointwise bounded. So by the principle of uniform boundedness, this has to be a supremum of norm of Jx X in B. This has to be finite. If it is pointwise bounded, then it is uniformly bounded. So, we get this. But what is the norm of Jx? Is same as norm of X. So, this will mean that this is same as supremum of norm X, X in B. So, supremum norm X is finite. That means that B is bounded. Right. So this is an interesting result that if for every bounded functional, the image of a set is bounded, then that set itself is bounded. And this is not true if you don't assume B to be a complete nonlinear space. The completeness is not there, then you can find example where this thing does not hold. Okay, any questions so far? All right. So next we will discuss the open mapping theorem. So let me state the theorem and then we'll see how to prove it. So the open mapping theorem says the following. Suppose V and W are both Banach spaces. Let V and W be Banach spaces and let T be a bounded linear transformation from V to W, and we will assume that T is onto. Let T be VW be onto, then T is an open map. So that is T maps an open set. T maps open sets in V onto open sets in W. Right. So you know that T is given to be continuous, but continuous maps need not be open map. So continuity says that inverse image of open set is open, but here what we are saying is that image of open set should be open. So such a map is called open map. So this is saying that if we have any onto bounded linear operator between two Banach spaces, here it is important that V and W are both Banach spaces, and T is any bounded linear operator, and we are assuming that it is surjective, then T is an open map. So this is the open mapping theorem. We will see how to prove it. So for this, we will need one lemma. So let me state this lemma first, and then see how to prove the theorem using this lemma. So let V and W be Banach spaces. And let
So can we say that an open map is like a quotient map in like topology? We have this idea of quotient maps where U is open if and only if Q inverse U is open.
right. So I mean, but yeah, that is true, but it is not relevant here. So okay, so this lemma says that suppose I have two Banach spaces and T is a bounded linear uh, operator from V to W, and suppose this is onto. Then so what this lemma says that if you take any open ball in V and look at its image, so that is a subset of W. So it says that that is basically an open set. So which means that there exists some open ball. So let me write. So then there exists some constant c greater than 0 such that the open ball 0 centered at the origin and radius c in W, this is contained inside T of BV01, where this BV and BW are open balls in V and W. So I think previously I used the notation BXR to denote the closed ball and D for the open ball. But because I'm mostly following this book by case one now, so let us use that same notation. So this proof also I'm following Keswan's book. So we are looking at open balls. So this is saying that the image of the open ball contains an open ball of W. Right?
Sir,
Yes.
sir, this open wall of V, why it is the radius 1?
I'm taking radius 1. So this is the result I am saying. But then, of course, here you can take any radius and it will follow. Right? So maybe I'll write that also. So first I'll prove only for, say, once you prove for the unit ball, then you can prove for any radius also, because if I write BV of 0 comma say R, then that is same as R times BV of 0 1, right? And then because T is linear, T of R times this will be R times T of this. And then if you take instead of C by R, then that will work, right? So this lemma will imply that actually you can do for any radius ball of V also, it will be true, right? So
Okay, sir.
maybe let me write that remark. So if R is any positive real number, then there exists some constant that's called s bigger than 0, such that Bw of 0s is contained in T of Bv of 0 comma R. So why is this? So
Like by linearity, like we can choose
yeah,
S equal.
exactly. So this is because Bv of 0 R is nothing but R times Bv of 0 1, which implies T of BV0R is equal to R times T of BV01. And we know that T of BV01 contains an open ball. So this contains R times T of, sorry, this contains R times BW of 0C for some C, and that is same as BW of 0 comma RC, right? So you can take S equal to R times C, and then this is true. So now first let me show that by using this lemma we can prove the open mapping theorem, and then we will see how to prove this lemma. So proof of the open mapping theorem using the lemma. So what we have to show that T maps open sets in V onto open sets in W. So let G be an open set in V, we have to show that T of G is an open set in W. So we want to show that T of G is open set in W. That means that for every point in T of G, there should exist an open ball which is contained inside T of G. So let Y belongs to T of G. Then we want to show that there exists some open ball centered at Y which is contained inside T of G. That will prove that T of G is open. So if Y is in T of G, Y is equal to T of X for some X in G. Then Y is equal to T of X for some X belonging to G. And now we'll use that G is open. Since G is open in V, there exists some radius r greater than 0 such that x plus bv 0 comma r, because this is same thing as b v of x comma r. This is contained inside G. Right? This is just by the definition of open that there exists some radius such that open ball of radius r centered at x. This is contained inside G. But this BVXR can be written as x plus BV of 0R. So x plus BV of 0R is contained inside G. Now if we apply T on this, so this will imply Tx plus T of BV0R. This is contained inside T of G. Right? Because of the linearity, we have T of x plus this is Tx plus this, but Tx is nothing but y. So that is y plus T of BV0R is contained inside T of G. So we have got that y plus this set is contained inside T of G. Now by the lemma we know that this T of BV0R, this will contain some open ball. So I have already written the remark, so I don't have to again write this as R times this. So directly we can use that remark. So by the remark following lemma before, we get some s bigger than 0 such that bw of 0 comma s is contained inside T of bv of 0r. Right, this is what we said here, that T of bv of 0r contains some open ball centered at origin in W. So we get this, and therefore y plus bw 0s is contained inside T of G. Right, and this means that T of G is open. So that is, it's also same as bw of y comma s is contained inside T of G. Therefore, T of G is open. So once we have the lemma, then the proof is easy. So now we have to see how to prove this lemma. So again, for this lemma, it is enough to prove for unit ball, not for general art. So we want to show that the image of the unit ball of V contains some ball in W. Right? So, and there you will see that we will need the completeness of X as well as of V as well as W. So both V and W are assumed to be Banach spaces. So again, this bare category theorem will be used for proving this open mapping theorem, just like we use for the Banach-Steinhaus theorem. So before proving this lemma, let me just give some notation. So if A and B are subsets of a vector space V, we write A plus B. This notation I think we saw before also. So when I write the sum of two subsets, that means that we are looking at X plus Y, where X belongs to A and Y belongs to B. Also, if lambda is any scalar, then lambda times A means you take the scalar multiple lambda times X for every X in A. Right, so we can define sum of two subsets and also scalar multiple of a subset. Now, let me write this claim. If A is a convex set, then A plus A, sorry, A plus A is same as 2A. I mean, it might look like A plus A should be 2A always, but this is true only for convex set. So if A is a convex set, then A plus A is equal to 2A. This is what we claim. This is very easy to see. So first of all, if we take any element in 2A, then it is always in A plus A. So if Y belongs to 2A, then Y is equal to 2 times X for some X in A. Now 2 of X is same as, so therefore Y is equal to 2X is same as X plus X. So Y is equal to X plus X, which belongs to A plus A. So therefore, this 2A is a subset of A plus A. This is always true. Here we are not using the convexity. This is true, even if A is not convex. But for the other way, if we take any element in A plus A, we want to show that it is in 2A. Also, if x plus y, let me write some z belongs to A plus A, this implies z is equal to x plus y for some x in A and y in A. Now, how do I show that this is in 2A? If it can be written as 2 times something, right? So this is equal to, of course, 2 times half x plus half y, right? So this will belong to 2A if this half x plus half y is in A. So if we assume that A is convex, in fact, we need only midpoint convex, right? So if the midpoint of any two vector is in that set, then we know that half x plus half y belongs to A. So this belongs to 2A. So since A is convex, half x plus half y belongs to A, and this implies z is equal to 2 times half x plus half y belongs to 2A. Right, so A plus A is equal to 2A. So this was one simple thing that we noticed. Now let's prove the lemma. So we will first prove that there exists some constant such that we will show that there exists some c greater than 0 such that Bw of 0 comma 2c, this is contained inside T of Bv01 closure. What we have to show is that open ball of radius c is contained inside T of Bv01. So first we will show that if we take radius 2c, then this ball is contained inside the closure of this, and then we'll see that this will imply that the open ball of radius c will be contained inside this without the closure. So how to show this? So first of all, we are given that T is onto. So since T is onto, W is equal to union of let's write T of PV 0 comma n. So if we look at the image of open ball of radius n, then take the union. This is same as W, because any W is equal to T of x, because T is given to be onto. So therefore, for any x, norm of x will be less than equal to some n, right? So W is equal to the union of this thing. This is true because T is on 2. So we get this. Now what we have that this complete nonlinear space is union, countable union of for some subsets. So by the bare category theorem, we know that the closure of at least one of them has non-empty interior. So by the bare category theorem, there exists some n naught such that interior of TBV 0 comma n naught, this closure is non-empty. But BV of 0 comma n naught is nothing but n naught times BV of 0 n naught. So this implies interior of T of BV of 0 1 closure. This is non-empty. This is because this TBV 0 n naught closure is same as n naught times T of BV 0 1 closure. Right? This is again by the linearity of T. We can take this n naught out and then we get this. So if this has this closure has an interior point, then you get that there is an interior point for TBV01 closure. So suppose we have something here. So let y0 belongs to interior of TBV01 closure. So then by definition of interior, there exists some constant c greater than 0 such that b of y0 comma let's say 4c, this is contained inside TBV01 closure, right? So this belongs to the interior means that there exists some radius, positive radius, such that this open ball is contained inside this set, and we are writing this 4c. So if we have c, then we use c by 4 here. So we get this. Now we will let's see that this c will satisfy that BW of 0 comma 2c is contained in this. So why is that? So in particular, y0 belongs to T of BV01 closure, and if y0 is here, then minus y0 will also be there, because minus y0 if y0 is in this, then T of minus of that, if you take, then minus of BV01 is same as BV01. So therefore minus y naught is also in TBV01 closure. Now if I take any point in B y naught comma 4c, so this is the ball in W. So now if Z belongs to BW of y naught comma 4c, this is in this closure. So this Z can be written as y naught plus something, then Z is equal to y naught plus say some Z prime or some Z prime belonging to BW 04c. So this Z prime is in BW04c, and Z prime is Z minus y naught. So Z prime is Z minus y naught, which belongs to this is Z plus minus y naught, and we have Z is in this ball of radius 4c, and minus y naught is also there. So this belongs to T BV of 01 closure plus TBV of 01 closure. Right, because Z is in this ball of radius 4c, which is in here, and minus y naught is also there. So Z plus minus y naught belongs to this plus this. And what is this? So therefore, what was this? Z prime was any point in I should do the other way. So if I take any point in this ball, then Z is in there. So yeah. So let me change it a little bit. So if I write any Z prime in BW 04c, then Z is equal to y naught plus Z prime. This belongs to BW of y naught 4c, which is contained inside TBV01 closure. So this Z is in this, and Z prime can be written as Z minus y naught. So this is in this plus this. So this is true for any Z prime. So this implies that BW of 0 comma 4c This is contained inside 2 times T BV01 closure. This is because we are using that this plus this is same as 2 times. Maybe let me write this here. So note that is equal to 2 times since this is a convex set. Right, so that is easy to see that this is convex because BV01, this open ball in non-linear space is always convex, and because T is linear, so any linear map will map convex set to convex set. So this will be convex, and closure of any convex set is always convex. So this will be convex. So that is why we proved that result that for convex set A plus A is same as 2A. So we get this. And since this BW of 04C can be written as 2 times BW of 02C, this thing implies BW of 02C is contained inside T of BV of 01 closure. So this was the step 1 that we wanted to prove, that there exists some C such that ball of radius 2C is contained inside closure of the image of unit ball in V. Okay, I'm already overshooting the time, so I'll stop here. So in the next class, we'll prove the second step. So far what we have used is since we are using here bare category theorem, what we are using is that W is complete. So the completeness of W is used so far, but we have not used completeness of V yet. So we'll see that to the step 2 will be to show that now BW of 0 comma C will be contained inside the image of this unit ball without the closure. So for that we will use the completeness of V also. We will construct a Cauchy sequence, and then by the completeness we know that that will converge, and that is what we use for proving that. So I'll complete that tomorrow, and then we will see some more consequences of this open mapping theorem. And after that, if we have time, then we'll look at the closed graph theorem also.